Have you ever stood outside on a clear night, gazing up at the stars, and felt that strange tug at your curiosity, the quiet whisper that there's so much more out there than we could ever understand? The universe isn't just a vast, empty stage dotted with distant lights. It's alive with mysteries, secrets woven into the very fabric of reality itself. Today, we're pulling back the curtain on 35 mind-bending insights that reveal the universe's hidden life, truths so astonishing they'll make you question everything you thought you knew. Think about this for a moment. Every atom in your body was forged in the heart of a dying star. You are literally made of stardust, a living piece of cosmic history. But if that's true, what else is out there waiting to be discovered? Dark energy stretching the universe apart like an invisible hand, dimensions beyond our perception, or the eerie possibility that we might not be alone, yet the silence of the cosmos remains deafening. These aren't just science fiction concepts, they're real, tangible mysteries that scientists grapple with every day, and they're just the beginning of what we'll explore together. This journey isn't just about facts and figures, it's about the stories the universe is trying to tell us, the clues hidden in the way galaxies spin, the way particles behave, even the way time itself can bend. By the time we're done, you won't just see the night sky as a collection of stars, you'll see it as a living, breathing entity, pulsing with questions that demand answers. So let's begin, because the universe has been waiting for us to listen. First, let's wrap our minds around something truly bizarre. What if everything you see, touch, and feel is nothing more than an illusion? Scientists studying the deepest layers of reality have stumbled upon a theory so strange it sounds like science fiction: the holographic principle. Imagine the universe as a giant movie screen, projecting a three-dimensional world from a two-dimensional surface at the edge of existence. Every star, every galaxy, even your own thoughts, might just be data encoded on a cosmic boundary we can't even see. This idea didn't come from nowhere. It's rooted in the mind-bending math of string theory and black hole physics. When researchers study how information behaves at the quantum level, they've found hints that space-time itself might be pixelated, like a digital image, but on the smallest possible scale. If you could zoom in far enough, reality might dissolve into tiny, indivisible blocks of information, like the universe's version of computer code. Now, here's where it gets even wilder. If the holographic principle is correct, then concepts we take for granted like free will or the solidity of matter might be nothing more than shadows on the wall of a much deeper reality. It raises a haunting question. Are we living in a simulation? Some physicists argue that if the universe operates like a hologram, an advanced civilization could, in theory, have engineered it. But before you dismiss this as fantasy, consider that experiments with quantum gravity and particle collisions are already searching for evidence of this pixelated structure in the fabric of space-time. What's at stake isn't just a quirky theory, it's the very nature of existence. If reality is a projection, then the rules we think govern the cosmos might be more like guidelines, with something far stranger lurking beneath. The holographic principle doesn't just challenge our understanding of the universe, it forces us to rethink what it even means to be real. And if that doesn't make you look at the night sky a little differently, just wait, we're only getting started. If the holographic principle left you questioning reality, brace yourself, because the universe has another curveball to throw at us. Picture this: every galaxy, every star, even the very space between them is being stretched apart by an invisible force that defies gravity itself. We call it dark energy, and it's not just some faint whisper in the cosmos, it's the dominant player shaping the fate of everything we know. Back in the 1990s, astronomers made a discovery that turned cosmology upside down. They expected the universe's expansion to slow down over time, pulled back by gravity's relentless tug. Instead, they found the opposite. The cosmos isn't just growing, it's accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing second. That hand is dark energy, a force so baffling that even the brightest minds struggle to explain it. Here's what makes it so strange. Gravity pulls things together. Planets orbit stars, galaxies cluster in vast webs, but dark energy does the opposite. It pushes relentlessly, as if space itself has a built-in repulsive force. And the wildest part, the more the universe expands, the stronger dark energy seems to become. It's like blowing up a balloon that inflates faster the bigger it gets, with no limit in sight. Some theories suggest dark energy might be woven into the very fabric of empty space, a property of the vacuum itself, growing more potent as the cosmos stretches. Others speculate it could be an entirely new kind of field or particle, something beyond our current physics. But one terrifying possibility looms over all of them: the Big Rip. If dark energy keeps strengthening unchecked, it could eventually overcome every force holding matter together. Galaxies would first be torn from one another, then stars from their galaxies, planets from their stars, until finally, even atoms themselves are ripped apart at the seams. Yet for all its power, dark energy leaves almost no trace. It doesn't glow, it doesn't collide, it doesn't clump. It's everywhere and nowhere at once. Astronomers hunt for clues in the vast voids between galaxies, where its effects are most pronounced, but the answers remain elusive. Why does this force exist? Is it a constant of nature, or could it change over time? The more we learn, the more we realize how little we truly understand about the universe's hidden architecture. Dark energy isn't just a cosmic mystery, it's a reminder that the universe plays by rules we're only beginning to glimpse. And if something this fundamental is still beyond our grasp, what other secrets lie waiting in the dark? We take time for granted: the steady tick of seconds, the unshakable order of past, present, and future. But what if it's all an elaborate illusion? Down in the quantum realm, where particles dance to rules that defy common sense, time doesn't behave the way we think it should. In fact, it might not exist at all. Picture an electron spinning in an atom. At this scale, particles don't just move from point A to point B like billiard balls. They exist in a haze of possibilities, occupying multiple states at once until something forces them to choose. Here's the strange part: this quantum superposition isn't bound by time. A particle can be in two places, spinning in opposite directions, without any concern for the sequence of events. It's as if time, the very framework of our daily lives, simply doesn't apply. Even stranger is entanglement, that eerie phenomenon where two particles become linked, instantly influencing each other no matter how far apart they are. Einstein called it spooky action at a distance, but the real spookiness might be what it reveals about time. Some physicists argue that entanglement doesn't just ignore space, it ignores time too. Experiments show that measuring one entangled particle can retroactively affect its partner, as if the future is reaching back to tweak the past. This has led to a radical idea: time isn't fundamental. Instead, it might emerge from the tangled web of quantum connections, a kind of cosmic mirage created by the relationships between particles. Think of it like watching a movie. The story has a clear sequence: beginning, middle, end, but the film itself is just frames on a reel. If you could step outside the universe, would you see time as another dimension, or just a pattern woven from deeper, timeless interactions? The implications are staggering. If time is fluid at the quantum level, then cause and effect, the bedrock of reality, might be more like guidelines than unbreakable laws. Could the past and future exist simultaneously, with the present just a fleeting slice of a timeless whole? Some theories even suggest that the Big Bang wasn't the true beginning, but a moment when time crystallized out of something far more mysterious. Of course, this doesn't mean clocks stop working or deadlines vanish. In our everyday world, time's arrow still points forward, but the quantum realm whispers a tantalizing secret. Beneath the surface, the universe might not care about before or after at all. And if that's true, then free will, memory, even the nature of existence itself, all of it might need a rewrite. The next time you check your watch, remember, you might not just be measuring time. You might be measuring an illusion. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them circled by planets in the so-called Goldilocks zone, where conditions are just right for life. Given those staggering numbers, the math seems undeniable. Alien civilizations should be out there, their signals crisscrossing the cosmos, their artifacts drifting between the stars. And yet, when we listen, when we search, all we hear is silence. This eerie absence of extraterrestrial voices is known as the Fermi paradox, and it's one of the most unsettling puzzles in science. Enrico Fermi, the brilliant physicist who first posed the question, put it bluntly: where is everybody? If the universe is so old and so large, why haven't we encountered even a single whisper of another civilization? The answers scientists have proposed range from the sobering to the downright spine-chilling. One possibility is that intelligent life is incredibly rare, that despite the countless planets, the chain of events needed to produce a technological civilization is so fragile, so improbable, that we might truly be alone. Think about that for a moment. In all this cosmic expanse, there might be no one else to share it with. But other theories are even more unsettling. Some suggest that advanced civilizations inevitably reach a point where they destroy themselves, whether through war, environmental collapse, or technologies they can't control. It's a grim thought that the universe might be littered with the ruins of societies that burned too brightly and faded too soon. Then there's the cosmic zoo hypothesis, the idea that alien civilizations know we're here but are deliberately avoiding contact, observing us like animals in a vast interstellar preserve. Maybe they're waiting for us to reach a certain level of maturity before revealing themselves, or maybe they see us as too primitive, too dangerous to engage. And then there's the most mind-bending possibility of all, that we're living in a simulation and the silence is just part of the programming. If reality is a construct, then the absence of aliens might be by design, a deliberate limitation to keep the simulation manageable. It sounds like science fiction, but some respected thinkers argue it's a plausible explanation for the Great Silence. Whatever the answer, the Fermi paradox forces us to confront profound questions about our place in the universe. Are we the first, the last, or is the cosmos hiding something even stranger from us? The silence isn't just empty space, it's a mirror, reflecting back our deepest hopes, fears, and uncertainties about what it means to exist in this vast, mysterious expanse. And until we find an answer, that silence will keep haunting us, whispering the same unshakable question: are we really alone? Black holes aren't just cosmic vacuum cleaners. They might be the universe's best-kept secret, hiding gateways to realities beyond our wildest imagination. Picture this, a place where gravity is so overwhelming that space and time twist into knots, where the rules of physics as we know them cease to exist. At the heart of every black hole lies a singularity, a point of infinite density where the fabric of reality itself seems to tear apart. But what if that tear isn't an end? What if it's a doorway? The idea isn't as far-fetched as it sounds. Einstein's equations of general relativity hinted at the existence of wormholes, hypothetical tunnels through space-time that could connect distant parts of the universe or even bridge entirely separate realities. And black holes, with their extreme warping of space-time, might just fit the bill. Imagine falling into one, and instead of being crushed into oblivion, you're funneled through a cosmic shortcut, emerging in another universe where the laws of physics play by entirely different rules. Here's where it gets even stranger. Quantum mechanics suggests that information, the fundamental building blocks of reality, can't be destroyed, even in a black hole. So where does it go? Some theorists propose that it's not lost at all, but encoded on the event horizon like a cosmic hard drive, then ejected back into the universe as the black hole slowly evaporates over eons. Others go further, suggesting the information is transmitted or even transformed into another reality altogether. Think of black holes as cosmic recyclers. Instead of being dead ends, they could be birthing new universes in their depths, where the matter and energy they consume re-emerge as the raw ingredients for an entirely new cosmic story. It's a dizzying thought. Every black hole might be a creator, not just a destroyer, spinning off new realms with their own laws and histories. Of course, we can't peer beyond an event horizon to test these ideas, at least not yet. But the math hints at possibilities that defy our everyday intuition. If black holes truly are portals, then the universe might be far more interconnected than we ever dreamed. The next time you look up at the night sky, remember, those dark, silent voids might not just be swallowing light, they might be weaving new realities in the shadows. What if everything you know, every decision you've ever made, every twist of fate that shaped your life, is just one thread in an infinite tapestry of possibilities? The multiverse theory isn't just a wild thought experiment. It's a serious scientific proposition that suggests our universe might be one of countless others, each with its own unique rules, histories, and even versions of you. Picture a cosmic kaleidoscope where every twist creates a new reality, a new universe where the laws of physics play out differently. In one, gravity might be stronger, crushing stars into black holes before life can emerge. In another, matter might never have clumped together at all, leaving an eternal sea of particles drifting in the dark. This idea doesn't come from science fiction. It springs from the hard math of quantum mechanics and inflationary cosmology. When the universe burst into existence during the Big Bang, space-time may have expanded so rapidly that pockets of it pinched off into separate bubbles, each becoming its own self-contained universe. Think of it like a pot of boiling water, bubbles forming, rising, and drifting apart, each one a universe with its own destiny. And just as bubbles in a pot never stop forming, new universes might be budding off from ours even now, in dimensions we can't perceive. Here's where it gets personal. If the multiverse is real, then somewhere out there, another version of you might exist. One who took that job you turned down, or missed the train you caught, or lived in a world where dinosaurs never went extinct. These parallel realities wouldn't just differ in small ways. They could be unrecognizable, with alternate histories, different constants of nature, or even extra dimensions folded into their fabric. The multiverse doesn't just suggest that anything is possible. It implies that everything is happening somewhere in some form. But how could we ever prove it? Some physicists look for bruises in the cosmic microwave background, scars left by collisions with other universes in the distant past. Others search for anomalies in the way particles behave, tiny deviations that might hint at forces leaking in from neighboring realities. And then there's the unsettling idea that black holes, those cosmic gateways we discussed earlier, might be birthing new universes in their cores, spinning off fresh branches of the multiverse with every collapse. The implications are staggering. If the multiverse is real, then concepts like fate, uniqueness, or even the meaning of life take on a whole new dimension. Are we just one iteration of an infinite series, or is there something special about our particular universe? The multiverse doesn't just expand the boundaries of reality, it shatters them, leaving us with a humbling truth. The cosmos might be far stranger, far grander, and far more mysterious than we ever dared to dream. Right now, as you sit there watching this, trillions of invisible cosmic messengers are passing straight through your body like ghosts walking through walls. These are neutrinos, the universe's most elusive particles, and they're so insubstantial that they barely interact with matter at all. Imagine holding a net with holes so wide that even the smallest fish could swim right through. That's what the entire Earth is to a neutrino, just empty space. These ghostly particles aren't just oddities, they're born in the most violent events the cosmos has to offer. When a star explodes in a supernova, when black holes shred matter into plasma, or when nuclear reactions rage in the heart of the sun, neutrinos are the first witnesses, racing outward at nearly the speed of light. Unlike light, which can be blocked or scattered, neutrinos travel unimpeded, carrying pristine information about their origins across billions of light years. They're cosmic telegrams stamped with the fingerprints of distant cataclysms. Catching these phantoms is no easy feat. Scientists build massive detectors deep underground, shielded from other particles by miles of rock. Some labs use Olympic-sized pools filled with ultra-pure water, waiting for the rare moment a neutrino bumps into an atom and creates a tiny flash of light. Others employ tanks of liquid argon, so sensitive they can spot the faintest ripple of a neutrino's passage. It's like listening for whispers in a hurricane. You need perfect silence and unimaginable patience. But why go to such extremes? Because neutrinos might hold the keys to physics' greatest mysteries. The Standard Model, our best theory of how particles behave, predicts neutrinos should be massless, yet experiments show they have a tiny, inexplicable weight. This discrepancy hints at entirely new physics, perhaps even extra dimensions or hidden particles we've yet to discover. Some neutrinos seem to change identities mid-flight, morphing between three known types in a quantum dance we still don't fully understand. Then there's the mind-blowing possibility that some neutrinos didn't originate in our galaxy at all. High-energy neutrinos detected in Antarctica's Ice Cube Observatory may have come from active supermassive black holes in distant galaxies, carrying stories of environments so extreme they make our sun look tame. Others might be relics from the Big Bang itself, ancient travelers that have been wandering the cosmos since the first seconds of existence. What's most humbling is realizing how much of the universe operates just beyond our senses. While we go about our lives, these silent spectators slip through everything: our homes, our planet, even our bones, carrying secrets from the farthest reaches of space and time. Neutrinos don't just challenge what we know, they remind us that the cosmos is always speaking, even when we're just learning how to listen. We think of the moon as a silent, barren world, a place where time stands still. But hidden in the rocks brought back by the Apollo astronauts lies evidence of a far more dynamic past. Those gray, dusty samples carry a startling secret. Our moon once had a magnetic field, something scientists long believed impossible for such a small body. Imagine standing on the lunar surface billions of years ago, holding a compass that actually pointed somewhere. The moon, it turns out, was once alive with unseen forces. The mystery begins with magnetism. When molten rock cools in the presence of a magnetic field, its minerals align like tiny compass needles, freezing that field's direction into the stone. That's exactly what researchers found in lunar samples, rocks magnetized as if the moon had its own protective shield, much like Earth's. But here's the puzzle: planetary dynamos, the swirling molten cores that generate magnetic fields, require enormous heat and churning metal. The moon is simply too small to have retained that kind of energy for long. So how did it pull off this cosmic magic trick? One theory points to a fleeting era of lunar adolescence. In its youth, the moon's core might have been heated by radioactive elements or the lingering energy of its violent birth, when a Mars-sized object slammed into Earth and flung debris into orbit. For a few 100 million years, this molten core could have churned just enough to spark a magnetic dynamo before cooling into stillness, but even that explanation leaves gaps. The moon's magnetism persisted far longer than its size should have allowed, like a candle burning in a sealed room long after the oxygen ran out. Then there's the asteroid wildcard. Some scientists propose that colossal impacts didn't just scar the moon's surface, they might have temporarily supercharged its magnetism. Picture a city-sized space rock slamming into the lunar crust with such force that it vaporized rock into an electrically conductive plasma. For a brief window, this swirling soup could have acted like a makeshift dynamo, imprinting magnetism into nearby rocks before fading away. It's a cosmic version of striking a match, intense, fleeting, and brilliant. The implications ripple far beyond the moon. If small, rocky worlds can generate magnetic fields through unconventional means, then our search for habitable planets just got more interesting. Magnetic shields protect atmospheres from being stripped away by solar winds, a crucial ingredient for life as we know it. Exoplanets once dismissed as too small might now be back on the table, their potential hidden beneath surfaces we're only beginning to understand. But the biggest question remains: what else don't we know? The moon's dusty archives are far from fully read. Future missions could uncover rocks that rewrite the story yet again, revealing even stranger chapters in lunar history. Every crater, every boulder, every grain of regolith might hold clues to a past where the moon wasn't just Earth's quiet companion, but a world with its own hidden fire. The next time you look up at that pale disk in the sky, remember, it wasn't always so silent. And if the moon has secrets this profound, what other surprises are waiting in the darkness between the stars? Imagine two coins flipped simultaneously on opposite sides of the galaxy. No matter how far apart they are, they always land matching heads with heads, tails with tails. Now replace those coins with subatomic particles, and you've got quantum entanglement, one of the most baffling and beautiful phenomena in physics. This isn't just theoretical, it's been tested in labs across the world. Particles born from the same quantum event remain mysteriously linked, mirroring each other's states instantaneously, even if separated by the width of the universe. Einstein famously hated this idea, calling it spooky action at a distance, because it seemed to violate his sacred speed limit, the speed of light. Yet experiment after experiment has proven him wrong. So how does this cosmic magic trick work? At its core, entanglement suggests that space, the vast emptiness between stars and galaxies, might be a kind of illusion. When two particles become entangled, they stop behaving as individual objects and start acting as a single system, as if the distance between them doesn't exist. It's like tearing a piece of paper in half and sending one half to another galaxy. No matter how far apart they are, the two have still know they belong together. Some physicists believe this happens because entangled particles are tapping into a deeper layer of reality, one where space-time isn't the fundamental framework. Think of it like two puppets controlled by the same invisible strings. The puppets might seem separate, but their movements are synchronized because they're connected at a level we can't see. In this view, the universe isn't a collection of isolated objects but a vast, interconnected web where everything is subtly linked. The implications are staggering. If entanglement proves that space is an illusion, then concepts like here and there might be nothing more than convenient labels. It also opens the door to technologies that sound like science fiction. Quantum computers, for example, rely on entangled particles to perform calculations at speeds impossible for classical machines. Secure quantum communication could create unhackable networks where any attempt to spy on a message would instantly alert the sender. But the deepest mystery remains: why does entanglement happen? Some theories suggest hidden variables, unknown forces guiding particles behind the scenes. Others propose that entangled particles are accessing higher dimensions, folding space-time in ways we can't perceive. Then there's the radical idea that the universe is fundamentally non-local, meaning every part of it is instantly connected to every other part, with space just a surface-level appearance. Whatever the answer, entanglement forces us to confront a universe far stranger than we ever imagined, one where separation might be the greatest illusion of all. The next time you look at the stars, remember, the particles in your body could, in some unseen way, still be whispering to the particles in those distant suns. And if that doesn't make you question the nature of reality, what will? On a quiet August night in 1977, an astronomer named Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope when he saw something that made his heart skip a beat. A vertical column of numbers and letters so extraordinary, he circled it in red pen and scribbled a single, telling word beside it: "Wow." That scribble would become legendary, giving a name to one of the most enduring mysteries in the search for extraterrestrial intelligence. The signal itself was unlike anything ever recorded. A narrowband radio burst 30 times stronger than the background noise of space, lasting exactly 72 seconds before vanishing without a trace. What made it even more intriguing was its frequency: 1420 MHz, the precise wavelength of hydrogen, the most abundant element in the universe. If you were trying to get the attention of a cosmic neighbor, this would be the galactic equivalent of shouting into the void on the clearest channel possible. For decades, scientists have chased possible explanations. Some argue it was a natural phenomenon, perhaps a comet's hydrogen cloud reflecting sunlight, or a bizarre astrophysical event we've yet to understand. Others point out that the signal's intensity and frequency suggest something far more deliberate. Unlike random cosmic noise, it had the hallmarks of a targeted transmission: narrow, focused, and eerily intentional. Yet the most haunting detail isn't what we know, it's what we don't. Despite countless searches, the WOW signal never repeated. No echo, no follow-up, no pattern. It's as if the universe teased us with a single, cryptic postcard before slipping back into silence. SETI researchers have scanned the same patch of sky near the constellation Sagittarius hundreds of times, hoping for another whisper. But space keeps its secrets well. Theories abound. Could it have been a one-time burst from an alien beacon, sweeping past Earth like a lighthouse beam in the dark? Or was it a fleeting glitch in our own technology, a cosmic prank played by the universe itself? The truth is, we may never know. But the WOW signal remains a humbling reminder of just how vast and unexplored the cosmos truly is. Perhaps the most profound question isn't about the signal's origin, but what it represents. That fleeting moment when humanity peered into the abyss and thought, just for a second, that the abyss might have peered back. And until we get another message, that 72-second mystery will keep us staring at the stars, wondering who or what might be out there waiting for us to listen. In the vast emptiness between the stars, where the sun's light fades to a dim glimmer, two tiny spacecraft named Pioneer 10 and 11 were silently rewriting the rules of physics. Launched in the early 1970s, these intrepid probes were humanity's first emissaries to the outer solar system, destined to drift forever among the stars. But as they ventured beyond Pluto, something bizarre happened. They began slowing down just a fraction more than anyone had predicted. At first, the discrepancy was minuscule, barely worth a second glance. But over years, then decades, that tiny anomaly grew into one of the most stubborn mysteries in space exploration, the Pioneer Anomaly. Imagine throwing a baseball and watching it slow down midair as if an invisible hand were gently tugging it backward. That's essentially what happened to the Pioneers. Despite meticulous calculations accounting for the sun's gravity, planetary tugs, even the drag of interstellar dust, the probes were decelerating by about 300 thousandths of a centimeter per second squared, a deviation so small you'd need a cosmic microscope to spot it. Yet in the precision-driven world of astrophysics, even a whisper of unexpected force demands an explanation. For years, theories swirled like solar winds. Could it be dark matter's gravitational pull subtly bending the probe's paths? Or perhaps an undiscovered planet lurking in the solar system's shadows, its gravity nudging the spacecraft off course? Some even dared to suggest a flaw in Einstein's theory of relativity, that gravity itself might behave differently in the icy void beyond Neptune. The Pioneer Anomaly wasn't just a scientific puzzle. It was a crack in the foundation of our cosmic understanding, threatening to widen with every unanswered question. Then came the breakthrough, one born not from grand cosmic revelations, but from the humblest of sources, heat. The Pioneers, powered by radioactive plutonium, glowed faintly with warmth, and that warmth turned out to be their undoing. Engineers realized the probe's own heat radiation, bouncing off their asymmetrical surfaces, was creating a tiny but measurable push, like a car's exhaust gently recoiling against its engine. This thermal recoil was the invisible hand slowing the Pioneers, a force so subtle it had eluded detection for decades. Yet the story doesn't end there. Because while the Pioneer Anomaly was solved, it left behind a haunting question. How many other invisible forces are acting on our spacecraft, hidden in the noise of cosmic uncertainty? Today, as newer probes like New Horizons streak toward interstellar space, scientists watch closely for any hint of fresh anomalies. Every unexpected twitch, every minor deviation could be the first clue to something far stranger, a force we haven't named, a law we haven't written. The Pioneers taught us a profound lesson. The universe doesn't give up its secrets easily. Even in the emptiness between stars, there are whispers of the unknown, tiny nudges that remind us how much we have yet to learn. So the next time you gaze at the night sky, remember out there, beyond the edge of our solar system, two silent explorers are still drifting, still carrying the echoes of a mystery that once defied physics. And who knows what other surprises are waiting in the dark? We think we know what the universe is made of: stars, planets, swirling galaxies, but these glittering objects are barely the tip of the cosmic iceberg. In fact, everything we can see, touch, and measure accounts for just 5% of the universe's total mass and energy. The rest, a shadowy realm of dark matter and dark energy, invisible forces shaping the cosmos behind the scenes. But here's the twist: even that measly 5% isn't fully accounted for. Nearly half of it has gone missing, vanishing into the cosmic ledger without a trace. Where could it be hiding? One leading theory points to vast, spiderweb-like structures called the cosmic web, threads of hot, diffuse gas stretching between galaxies, so faint they're nearly impossible to detect. Picture the universe as a network of interconnected highways with galaxies clustered at the intersections. The roads themselves, those thin strands of gas, might contain more ordinary matter than all the stars in the sky combined. But because this gas is so spread out, just a few atoms per cubic meter, it barely registers on our telescopes, like trying to spot a single snowflake in a blizzard. Then there's the intergalactic medium, the sparse soup of particles floating in the voids between galaxy clusters. For decades, astronomers assumed these regions were near empty, but recent observations suggest they might be teeming with ionized hydrogen and helium, remnants of the Big Bang. This gas isn't just faint, it's scorching hot, glowing in X-rays rather than visible light, which explains why it stayed hidden for so long. Satellites like the Chandra X-ray Observatory have begun mapping these invisible reservoirs, revealing a hidden skeleton of matter woven through the cosmos. But the plot thickens. Some of this missing matter might not even be in gas form. Tiny, cold clouds of molecular hydrogen could be drifting undetected, too cool to emit light yet too sparse to block the light passing through them. Others speculated could be tied up in rogue planets, black holes, or even exotic particles we haven't yet discovered. The truth is, we're still piecing together a puzzle where half the pieces are deliberately hiding from us. Why does this matter? Because this missing 5% isn't just a bookkeeping error, it's the blueprint of the universe. The way matter clumps and flows determines how galaxies form, how stars ignite, and ultimately, how life finds a foothold. If we can't account for it, our models of cosmic evolution are fundamentally incomplete. It's like trying to understand a painting when half the canvas is blank. The search for this lost matter isn't just about filling gaps in a spreadsheet. It's a reminder of how much we still don't see, even in the familiar corners of the universe. The next time you look up at the night sky, remember, the stars are just the glittering crumbs of a much larger, stranger feast, and we're only beginning to set the table. Picture this: you wake up one morning, memories intact, the world around you perfectly consistent, only to realize none of it actually exists. Your entire life, every person you've ever known, even the universe itself, is nothing more than a random flicker of atoms, a fleeting hallucination conjured by chaos. This isn't the plot of a sci-fi movie, it's the Boltzmann brain paradox, one of the most unsettling thought experiments in physics, and it forces us to question whether anything we experience is real. The idea comes from Ludwig Boltzmann, a 19th-century physicist who grappled with the nature of time and entropy. He theorized that in an infinitely old universe where particles randomly collide over eternity, even the most improbable events must eventually happen. Given enough time, a fully formed, self-aware brain could spontaneously assemble from quantum noise, complete with fabricated memories and a phantom reality. Not just once, but countless times. Statistically, these Boltzmann brains should vastly outnumber real, biologically evolved minds like ours. So why do we assume we're the genuine articles and not just momentary glitches in the cosmic noise? Here's where it gets even stranger. Modern cosmology suggests the universe might be headed toward a heat death, a state of maximum entropy where all energy is evenly spread and no meaningful work can be done. In this cold, dark future, Boltzmann brains become even more likely isolated consciousnesses blinking in and out of existence, each convinced they're living in a real universe. Some versions of the paradox even suggest these phantom minds would outnumber real observers by an unimaginable margin, making it astronomically more probable that you are one of them. But the paradox cuts deeper than just a fun brain teaser. It challenges the foundations of how we understand reality. If our memories and perceptions can't be trusted, if we might just be accidental fluctuations, then science itself becomes untethered. Every experiment, every observation could be part of an elaborate illusion. It's like realizing the detective in a mystery novel might be the killer, and the clues were planted to deceive even him. Some physicists argue the paradox points to flaws in our cosmological models. Maybe the universe isn't infinitely old, or perhaps there's a deeper principle preventing Boltzmann brains from forming. Others suggest it's evidence for the multiverse that our reality is just one bubble in a frothing cosmic sea, where the conditions for life are finely tuned. Then there's the haunting alternative, that the paradox is unsolvable, and we're left forever wondering whether we're the universe's intended guests or just ghosts in its machine. What makes the Boltzmann brain paradox so gripping isn't just the science, it's the existential vertigo it induces. Stare at it too long, and you start to question the fabric of your own existence. But here's the twist. The very fact that we're here debating this might be the best evidence against it. Conscious observers in a Boltzmann universe would almost certainly experience incoherent, fragmented realities, not the stunningly consistent cosmos we inhabit. The paradox might not prove we're illusions, but instead highlight how astonishingly real our universe seems to be. So the next time you feel the weight of your coffee cup in your hand, or hear the wind rustling through leaves, take a second to marvel at the unshakable consistency of it all. The Boltzmann brain paradox doesn't just ask whether we're real, it forces us to confront why reality feels so convincingly, beautifully solid in the first place. And if that doesn't make you pause, just remember, somewhere in the infinite chaos, another version of you might be having the exact same thought. The Milky Way isn't drifting through space aimlessly. It's racing toward something unseen at over 600 kilometers per second, caught in the grip of a cosmic mystery we can't even see. Hidden behind the thick dust clouds of our own galaxy's center, an enormous gravitational anomaly lurks, pulling millions of galaxies toward it like moths to a flame. Astronomers call it the Great Attractor, and it's one of the most perplexing enigmas in modern cosmology. What makes this force so puzzling is its invisibility. Normally, when we observe galaxies moving en masse, we can spot the culprit, a colossal cluster or supercluster of visible matter exerting gravitational influence. But the Great Attractor defies this expectation. Even with our most advanced telescopes, the region appears strangely empty compared to the sheer strength of its pull. It's as if the universe is playing a trick on us, hiding the hand that's tugging at the cosmic strings. One leading theory suggests the attractor might be the heart of the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with our Milky Way sitting on its outer fringe. In this scenario, the collective gravity of countless galaxies, some shrouded by interstellar dust, could explain the motion we observe. But here's the catch. Even adding up all the visible matter in Laniakea falls short of accounting for the attractor's immense pull. There's something else at work, something we can't yet see. That missing piece might be dark matter, the universe's invisible scaffolding. Some researchers propose the Great Attractor could be anchored by an unusually dense knot of this mysterious substance, warping space-time on a scale that bends the paths of entire galaxies. Others speculate about even stranger possibilities, like primordial black holes left over from the Big Bang or cosmic defects in the fabric of reality itself. But the biggest challenge is simply getting a clear look. Our view toward the attractor is blocked by the Milky Way's own galactic plane, a zone so packed with gas and dust that visible light can't penetrate. It's like trying to peer through a blizzard to spot a distant mountain. To overcome this, astronomers turn to infrared and radio telescopes, which can cut through the obscuring haze. Projects like the Square Kilometre Array are poised to map this hidden realm in unprecedented detail, potentially revealing whether the attractor is a familiar structure in disguise or something far more exotic. What's at stake isn't just solving a celestial whodunit. It's about understanding the forces that shape our cosmic neighborhood. The Great Attractor isn't just pulling galaxies. It's pulling at the boundaries of our knowledge, reminding us how much of the universe remains hidden in plain sight. And until we lift that veil, we're left with a humbling truth. Even as we rush toward this mystery at millions of kilometers per hour, the answers seem to stay just out of reach. The universe is supposed to be isotropic, the same in all directions, no special axis, no cosmic up or down. But when scientists mapped the cosmic microwave background, the faint glow left over from the Big Bang, they stumbled onto something that shouldn't exist, a strange, ghostly alignment between the CMB's largest fluctuations and the plane of our solar system. They called it the axis of evil, not because it's malevolent, but because it threatens one of cosmology's most sacred assumptions, that the universe has no preferred direction. At first glance, the CMB looks like a random splatter of hot and cold spots, a snapshot of the infant universe's density variations. But when researchers analyzed it in detail, they found these fluctuations weren't entirely random. Some of the largest patterns seemed oddly aligned with our solar system's ecliptic, as if the universe had quietly drawn a giant arrow pointing right at us. The odds of this happening by chance are astronomically low, like shuffling a deck of cards and dealing yourself a perfect royal flush over and over again. This isn't just a quirky statistical hiccup. If the axis of evil is real, it implies the universe might have a built-in orientation, a cosmic north that defies everything we thought we knew about the Big Bang's aftermath. One radical explanation suggests the anomaly could be an imprint from before the Big Bang, a scar left by some earlier phase of reality, like a fingerprint pressed into the fabric of space-time itself. Others propose it's evidence of a multiverse, where our universe is just one bubble among countless others, and the axis marks where we brushed against a neighboring cosmos. Then there's the unsettling possibility that we're seeing a cosmic illusion. Could the axis be a trick of perspective, a distortion caused by something between us and the CMB? Some theorists point to dark energy or primordial magnetic fields as potential culprits, warping the ancient light on its 14 billion-year journey to our telescopes. But so far, no conventional explanation fully accounts for the signal's strength and scale. What makes the axis of evil so compelling isn't just the mystery, it's the defiance. The universe isn't supposed to play favorites, yet here we are, staring at a pattern that feels eerily deliberate. Future missions like the European Space Agency's Cosmic Origins Explorer could settle the debate, mapping the CMB with unprecedented precision to confirm whether the axis is a fluke or a fundamental rewrite of cosmic history. Until then, it stands as a humbling reminder. Even the oldest light in the universe still has secrets to spill. And if something as basic as direction isn't what we thought, what other cosmic certainties are waiting to be overturned? If black holes are the universe's ultimate vacuum cleaners, then white holes would be their explosive counterparts, cosmic fire hydrants blasting matter and energy outward with unstoppable force. These bizarre objects aren't just science fiction. They emerge naturally from Einstein's equations as the mathematical opposites of black holes. Where a black hole's event horizon is a one-way street into oblivion, a white hole's boundary would be an exit door nothing can enter, only escape. Picture a waterfall running backward, defying gravity to hurl water upward in a dazzling, impossible spray. That's the kind of cosmic defiance we're talking about. The irony is that while black holes are everywhere, lurking in galaxy centers, hiding in binary star systems, white holes remain stubbornly theoretical. No telescope has ever caught one in the act, but here's where it gets fascinating. Some physicists argue we might have already witnessed a white hole and just didn't realize it. Take gamma-ray bursts, those fleeting but unimaginably violent explosions that light up the cosmos. Could some of them be white holes momentarily punching through the fabric of reality, ejecting their contents before snapping shut like a cosmic trapdoor? Then there's the ultimate white hole candidate, the Big Bang itself. Think about it, a singularity erupting outward, creating space, time, and everything we know in an instant. If a black hole is a universe collapsing inward, the Big Bang fits eerily well as its mirror image, a white hole birthing a cosmos. This idea, sometimes called the Big Bounce theory, suggests our universe might be one link in an endless chain, each cycle beginning with a white hole's outburst and ending with a black hole's collapse. But white holes don't just rewrite cosmic history, they threaten to upend physics' most sacred rule, entropy, the inevitable slide toward disorder. Black holes are entropy's enforcers, swallowing information and energy into chaos. White holes, by contrast, would defy this flow, spewing out pristine, low-entropy material like a magician pulling endless rabbits from a hat. If they exist, they'd imply that time's arrow isn't as fixed as we thought, that somewhere in the universe the thermodynamic clock might actually run backward. The most tantalizing possibility, white holes could be wormholes in disguise. Einstein's math allows for a black hole's interior to connect to a white hole's exit via a space-time tunnel, offering a shortcut across the universe, or even to another universe entirely. The catch, surviving the trip, is another matter. The gravitational forces and radiation near a white hole's maw would likely shred anything approaching it, turning this cosmic gateway into a deadly one-way street. So why haven't we found one? Maybe they're too fleeting, blinking in and out of existence before our telescopes can catch them. Or perhaps they're camouflaged as something else: quasars, pulsars, or even dark matter anomalies. Whatever the answer, white holes remind us that the universe loves symmetry, even when it defies logic. The next time you hear about a mysterious cosmic explosion, ask yourself, could that be a white hole winking at us from the edge of reality? Our galaxy isn't just a tranquil whirlpool of stars, it's a cosmic pressure cooker with a violent past, and the proof is written in the sky. In 2010, astronomers analyzing data from the Fermi Gamma-Ray Space Telescope stumbled onto something breathtaking: two colossal bubbles of scorching hot gas, each towering 25,000 light-years above and below the Milky Way's disk. These aren't just any structures, they're seething with gamma rays, the universe's highest energy light, like a pair of ghostly lungs exhaling radiation into the void. What could possibly create something so immense? The leading suspect is Sagittarius, a star, the supermassive black hole squatting at the galaxy's heart. Black holes aren't just passive vacuum cleaners, they're cosmic engines, capable of erupting in titanic outbursts when they feast on too much gas and dust. Picture a dormant volcano suddenly blasting a column of ash miles into the sky. Only this eruption would have been powerful enough to fling matter clear across the galaxy, carving out these bubbles like a cosmic blowtorch. The energy required is almost beyond comprehension, millions of times more violent than a supernova, a detonation felt across the entire Milky Way. But there's another possibility, a frenzy of star formation so intense it triggered a chain reaction of supernova. Imagine a stellar nursery on steroids, birthing thousands of massive stars in a short-lived frenzy. These stars would burn bright and die young, exploding in rapid succession, their combined shock waves inflating the bubbles like a balloon in a hurricane. Either scenario paints a picture of a galaxy far more dynamic and far more volatile than we once believed. The real mystery isn't just what caused the bubbles, but when. Based on their size and the speed of their expansion, this cataclysm likely occurred somewhere between 6 and 26 million years ago, a blink in cosmic time, back when early ancestors of humanity were just beginning to walk upright. And here's the haunting part, there's no guarantee it won't happen again. Sagittarius, a star, is relatively quiet now, but if another gas cloud or star wanders too close, it could spark another eruption, one that would light up the galaxy in a blaze of radiation visible clear across the universe. What's most humbling is how long these bubbles went unnoticed. Hidden in plain sight, their faint glow was drowned out by the Milky Way's brighter features until Fermi's sensitive instruments peeled back the veil. It makes you wonder what other colossal structures are lurking just beyond our perception, waiting for the right tool, the right moment to reveal themselves. The Fermi bubbles aren't just relics of the past. They're a reminder that even our home galaxy, the one we think we know best, still has the power to shock us. And if something this enormous could stay hidden for so long, what else is out there waiting to be discovered? When astronauts placed seismometers on the moon during the Apollo missions, they expected to record gentle tremors, maybe the occasional meteorite impact or the moon's crust settling over time. What they got instead were readings so bizarre they sparked whispers of something far stranger. The moon didn't just vibrate, it rang, resonating for hours after impacts like a colossal bell struck by a cosmic hammer. These seismic echoes lasted up to 10 times longer than anything observed on Earth, as if the moon's interior was hollow or filled with vast, empty chambers. Mainstream science has explanations, of course. The moon's dry, rigid structure lacks water or atmosphere to dampen vibrations, allowing quakes to reverberate unnaturally long. Its crust is also fractured from eons of meteorite bombardment, creating networks of cracks that could amplify seismic waves. But even accounting for these factors, the moon's behavior remains oddly exaggerated. Its density, roughly 60% that of Earth, suggests it isn't just lighter. It might be structured differently, with pockets of emptiness hidden beneath its dusty surface. One compelling theory points to ancient lava tubes. Billions of years ago, when the moon was volcanically active, rivers of molten rock may have carved out enormous tunnels that later collapsed or sealed shut, leaving behind labyrinthine caverns. Some of these tubes could be massive, wide enough to swallow entire cities, their ceilings arched like cathedral vaults. Future lunar explorers might stumble into these shadowy voids, finding underground networks untouched since the solar system's earliest days. Then there's the wilder idea that the moon's hollow signature isn't natural at all. A handful of conspiracy theorists, citing classified documents and alleged whistleblowers, claim the moon could be an artificial construct, a colossal spacecraft parked in orbit by some ancient intelligence. While there's zero credible evidence for this, it's hard to ignore the coincidences. The moon's size and distance from Earth create near-perfect solar eclipses, a cosmic fluke unique in our solar system. Its composition differs starkly from Earth's, lacking iron-rich metals in quantities that planetary formation models predict. But before we jump to extraterrestrial conclusions, consider another possibility. The moon might simply be a frozen relic of a violent birth. When the hypothetical planet Theia smashed into early Earth, the debris that coalesced into our moon could have formed with a porous, fragmented interior, like a cosmic sponge riddled with gaps from its traumatic origins. This wouldn't just explain the seismic oddities, it could rewrite our understanding of how moons form after colossal impacts. The truth is, we won't know for sure until we dig deeper, literally. Future missions equipped with ground-penetrating radar or seismic arrays could map the moon's subterranean voids in detail, revealing whether they're lava tubes, impact fractures, or something even more unexpected. Until then, the moon keeps its secrets close, a silent neighbor with a resonant mystery at its core. And whether hollow, honeycombed, or just hauntingly different, it reminds us that even the most familiar objects in the night sky can hide astonishing surprises. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there. a dark, elongated object moving so fast it couldn't possibly be bound by the sun's gravity. This wasn't just another asteroid or comet. It was our first confirmed visitor from interstellar space, a cosmic wanderer from another star system. They named it Oumuamua, Hawaiian for scout or messenger, and from the moment it was detected, it defied every expectation. First, there was its shape. Most asteroids and comets are roughly spherical or lumpy, but Oumuamua was different, long and thin, like a cosmic cigar, stretching perhaps 800 meters in length but only 80 meters wide. This bizarre geometry alone made it stand out, but then came the real shock. It wasn't just coasting. As it hurtled away from the sun, it accelerated slightly, as if pushed by some unseen force. Comets often speed up like this when their ices vaporize, creating jets of gas that act like natural thrusters, but Oumuamua showed no signs of outgassing. No tail, no coma, nothing. It was as if an invisible hand had given it a gentle nudge. Theories exploded almost as fast as the object itself. Some scientists proposed it might be a hydrogen iceberg, a chunk of frozen hydrogen gas that sublimated in sunlight, producing just enough thrust to explain the acceleration. But hydrogen ice is so fragile it's unclear how it could survive the journey between stars. Others suggested it could be a shard of a shattered planet, a piece of debris blasted into space by a cataclysmic collision in some distant system. Then there was the wilder idea: could Oumuamua be artificial? The absence of visible outgassing, combined with its unusual shape, led a few researchers to float the possibility it might be a derelict light sail, a piece of alien technology drifting through the cosmos. But here's the frustrating part: we'll likely never know for sure. By the time Oumuamua was spotted, it was already racing away, too distant for detailed observation. Telescopes scrambled to catch glimpses as it faded into the black, leaving behind a trail of unanswered questions. Was it a natural oddity or something more? The data we have is tantalizingly ambiguous, a Rorschach test for astronomers. Those who see a comet find ways to explain its behavior. Those who wonder about alien artifacts point to the gaps in our knowledge. What's undeniable is that Oumuamua shattered the assumption that interstellar visitors would resemble the comets and asteroids we know. If this is what's drifting between stars, then the universe is far stranger than we imagined. And if one scout has already passed through, how many more are out there, silent and dark, slipping unnoticed through the void? Future telescopes like the Vera Rubin Observatory will scan the skies for more of these nomads, hunting for clues to their origins. Until then, Oumuamua remains a mystery, a fleeting glimpse of the vast, uncharted wilderness beyond our solar system, and a reminder that sometimes the most profound discoveries are the ones that leave us with more questions than answers. Imagine waking up one day to discover that entire centuries of history were nothing more than an elaborate fiction, that the wars, kings, and cultural shifts you learned about never actually happened. This is the jaw-dropping claim of the phantom time hypothesis, a controversial theory suggesting roughly 300 years of the early Middle Ages specifically. The period between 614 and 911 were fabricated. According to this idea, we're not actually living in the 21st century, but somewhere closer to the early 1700s. The theory was first proposed by German historian Herbert Illig in the 1990s, and while it's been overwhelmingly dismissed by mainstream scholars, it forces us to confront something unsettling: how much of history is built on trust. Illig's argument hinges on perceived inconsistencies in the historical record, gaps in archaeological evidence, suspiciously neat chronological overlaps, and alleged errors in carbon dating techniques. He points to figures like Charlemagne, the towering emperor of the Holy Roman Empire, and suggests his legend might be an elaborate patchwork of myths and invented events designed to fill a manufactured timeline. But here's where it gets even more intriguing. Supporters of the hypothesis highlight oddities like the Gregorian calendar reform in 1582, where 10 days were skipped to correct drift in the Julian calendar. Could that adjustment have been covering up a far larger temporal discrepancy? Or consider the scarcity of surviving architectural and written records from the disputed period compared to earlier and later eras? Is that simply the result of time's erosion or evidence of a grand historical hoax? Mainstream historians counter with overwhelming evidence: tree-ring data from ancient wood, astronomical records of eclipses, and documents from civilizations outside Europe that align perfectly with the conventional timeline. Yet the phantom time hypothesis lingers not because it's likely true, but because it exposes the fragile scaffolding of historical knowledge. We rely on fragments, scraps of parchment, layers of sediment, the shifting interpretations of generations of scholars. What if key pieces were misplaced, misread, or manipulated? Beyond conspiracy, the theory taps into a deeper anxiety. Memory, whether personal or collective, is fallible. We stitch together the past from incomplete sources, trusting that the narrative holds. But history isn't just facts, it's a story we tell ourselves, and stories can be edited. The phantom time hypothesis may be a fringe idea, but it serves as a provocative thought experiment. How much of the past is set in stone, and how much is just a story we've agreed to believe? In the end, the real phantom might not be missing centuries, but our own certainty about what really happened. Right now, the universe is expanding at an accelerating rate, galaxies fleeing from one another as if trying to escape some invisible pull. But where does this cosmic sprint lead? The answer lies in a battle between two titanic forces: dark energy, relentlessly pushing space apart, and gravity, the silent architect trying to hold it all together. Depending on which one wins, the cosmos could meet one of two extraordinary fates: the icy stillness of heat death or the cataclysmic fury of the Big Crunch. Let's start with heat death, the current front-runner in this cosmic showdown. Picture a universe where every star has burned out, every black hole evaporated, and all matter has decayed into faint, scattered particles drifting endlessly in the dark. With no energy gradients left, no hot or cold, no high or low, the cosmos becomes a featureless sea of equilibrium. Time loses all meaning as there are no processes left to mark its passage. It's not a dramatic explosion or collapse, but a slow, quiet fade into oblivion, like embers cooling in a dead fire. This bleak outcome hinges on dark energy's dominance, its repulsive force growing stronger as space stretches, ensuring expansion never stops. But what if gravity fights back? If dark energy weakens over time? Or if there's more mass in the universe than we've accounted for, the tides could turn. Galaxies would begin creeping toward one another, their motion reversing as gravity regains the upper hand. At first, it would be subtle, a cosmic sigh after eons of outward breath. Then, acceleration would become collapse. Space itself would crumple like a sheet of paper, galaxies merging in violent bursts of light as the temperature of the universe skyrockets. Eventually, all matter would converge into a single, searing point, a mirror image of the Big Bang, known as the Big Crunch. It's the ultimate cosmic reset button, a singularity that might birth a new universe in its aftermath. This raises a tantalizing possibility. Could our universe be cyclical? Some theories suggest the Big Crunch might not be an end, but a rebirth. Like a phoenix collapsing into ashes only to rise again, the universe could undergo endless cycles of expansion and contraction, each iteration tweaking the laws of physics slightly differently. In this scenario, time has no true beginning or end, just an infinite loop of cosmic dawns and twilights. Yet the truth is we're still deciphering the rules. The fate of the universe depends on dark energy's true nature, and right now, it's an enigma wrapped in mystery. Does its strength remain constant, or could it decay over time? Is it even a single force, or are there layers we haven't uncovered? Every new observation, from distant supernova to the large-scale structure of galaxy clusters, adds another piece to the puzzle. What's most humbling isn't just the scale of these possibilities, but the reminder that our universe is fleeting by cosmic standards. Whether it ends in ice or fire, in trillions of years, all traces of human existence will be gone, erased by forces beyond our comprehension. The universe doesn't owe us permanence. It simply is vast and indifferent, playing out a story whose final chapter is written in laws we're only beginning to glimpse. And perhaps that's the most profound lesson of all, not just how the universe ends, but how rare and precious it is to witness even a single page of its epic. For decades, a shadowy figure has haunted Earth's orbit, an enigmatic object whispered about in conspiracy circles and dubbed the Black Knight satellite. Stories claim it's an alien probe, silently circling our planet for thousands of years, its origins lost to prehistory. The legend traces back to strange radio signals allegedly intercepted by Nikola Tesla in the 1890s, and odd echoes picked up by amateur radio operators in the 1920s. By the 1960s, newspaper headlines speculated about a mysterious dark satellite of unknown origin, and grainy NASA photos from the 1990s seemed to show a bizarre, angular shape floating against the blackness of space. The mythos was born, but here's the twist: the Black Knight almost certainly isn't what believers claim. Space agencies have repeatedly debunked the idea, pointing to far more mundane explanations. The satellite in those infamous NASA images, likely a thermal blanket lost during a spacewalk, its crumpled form catching sunlight in ways that made it look artificial. Those eerie radio signals, natural cosmic noise, or early human transmissions bouncing off the ionosphere. Even the timeline falls apart. No ancient civilization could have launched an object into orbit without leaving behind a mountain of technological evidence we'd have uncovered by now. Yet the legend endures, and that's the real mystery. Why does the idea of the Black Knight captivate us so deeply? Part of it taps into humanity's oldest storytelling instinct, the fear or hope that we're not alone. Ancient cultures wove tales of gods and celestial messengers. Today, we project those same yearnings onto grainy photos and unverified signals. The Black Knight is a Rorschach test for the space age, a blank screen onto which we project our anxieties about government secrecy, alien contact, and the vast unknowns lurking just beyond our atmosphere. There's also the thrill of the unsolved. In an era where satellites map every inch of the globe and telescopes peer billions of years into the past, the idea that something could hide in plain sight, right above our heads, is irresistibly tantalizing. It's the same impulse that fuels fascination with Atlantis or UFOs, the possibility that history, as we know it, is incomplete. The Black Knight isn't just a story about aliens, it's a metaphor for all the truths we haven't uncovered yet. But perhaps the most revealing aspect is how the myth evolves. Every few years, new evidence surfaces, a distorted radio transmission, a blurry photo, and the cycle renews. In a way, the Black Knight is less about extraterrestrials and more about us. It reflects our hunger for wonder in a world where science has demystified so much. When we stare into the night sky, we don't just want a universe of empty space and cold equations. We want it to whisper back, and until it does, legends like the Black Knight will keep orbiting not just Earth, but our collective imagination. Have you ever seen a faint, ethereal glow stretching up from the horizon just after sunset or before dawn? A ghostly triangle of light that seems to cling to the path of the sun and moon. This isn't some trick of the eyes or atmospheric illusion. It's the zodiacal light, one of the most haunting and least understood phenomena in our night sky. Unlike the shimmering auroras or the sharp gleam of meteors, this glow is subtle, almost shy, visible only under the darkest, clearest conditions, but don't let its delicacy fool you. This whisper of light holds clues to some of the solar system's deepest mysteries. What creates this celestial apparition? The answer lies in an ocean of dust, countless tiny particles, some no larger than grains of sand, drifting along the same plane where the planets orbit. When sunlight hits these motes, they scatter its rays, painting that faint luminous wedge against the night. But here's where things get intriguing. No one's entirely sure where all this dust comes from. One theory points to the asteroid belt, where rocky bodies collide and grind each other down over eons, filling space with debris. Another suggests it's far older, a relic from the solar system's violent infancy, when swirling gas and dust coalesced into planets, leaving behind a primordial haze that's lingered for billions of years. The dust's distribution tells a story of its own. Instead of spreading evenly, it clusters in strange, asymmetrical patterns, hinting at unseen forces at work. Jupiter's massive gravity might be herding particles into certain orbits, while solar wind and magnetic fields could be sculpting the cloud into shapes we've only begun to map. Some researchers even speculate that interstellar dust drifting in from beyond our solar system could be mixing with the local supply, adding another layer to the puzzle. Studying this faint glow isn't just about solving a cosmic whodunit. It's a window into the chaos of the early solar system. The same processes that left this dust behind also built the planets, including Earth. By analyzing its composition, whether it's rich in silicates, metals, or organic compounds, we could uncover secrets about the raw materials that formed our world. Some of these particles might even predate the sun itself, frozen time capsules from the molecular cloud that gave birth to our entire neighborhood. But the zodiacal light isn't just a relic of the past. It's a dynamic, ever-changing phenomenon. New dust is constantly being added from comets shedding material as they swing close to the sun, or even from meteoroid impacts on airless worlds like the moon, kicking up fresh clouds of debris. The light we see today is a living record, a snapshot of an ongoing process that's been unfolding since the dawn of the solar system. The next time you find yourself under a truly dark sky, far from city lights, take a moment to look for this elusive glow. It's more than just a pretty sight, it's a message from the depths of space, written in sunlight and dust. And as we learn to read it, we might just find the answers to questions we haven't even thought to ask yet. Beyond Neptune's icy orbit, where sunlight dwindles to a faint glimmer, the Kuiper belt stretches like a cosmic junkyard, home to frozen worlds, dwarf planets, and primordial debris left over from the solar system's birth. But something strange happens when you reach about 50 astronomical units from the sun. The belt's population doesn't thin gradually, it plummets off a cliff. This sudden drop, known as the Kuiper cliff, defies everything we know about how planetary systems form. It's as if someone took a cosmic broom and swept the outer solar system clean, leaving behind only unanswered questions. One compelling explanation points to gravitational interference, the invisible hand of an undiscovered planet lurking in the darkness. This hypothetical world, often called Planet 9 or Planet X, would be massive enough to shepherd Kuiper belt objects into peculiar orbits while clearing out entire swaths of material. Computer simulations show such a planet 10 times Earth's mass and orbiting 20 times farther than Neptune could create exactly the abrupt edge we observe. The math works, but the planet itself remains frustratingly elusive, hidden somewhere in the vast expanse of our solar system's uncharted backyard. Then there's the stellar intruder theory. Roughly 4 billion years ago, during the solar system's chaotic youth, a rogue star might have barreled through our cosmic neighborhood. This close encounter would have been a gravitational catastrophe, flinging comets inward while stripping away the Kuiper belt's outer layers like a tidal wave scraping a beach clean. Evidence for this scenario comes from oddly tilted orbits in the outer solar system, and the fact that many nearby stars show similar flyby scars in their own debris disks. It's a cosmic hit and run that could explain why our solar system's edge looks so unnaturally sharp. But the most tantalizing possibility is that we're seeing echoes of the Sun's birth cluster. Most stars form in dense stellar nurseries surrounded by siblings, and our Sun was likely no exception. In its early days, gravitational tugs from these sibling stars could have sculpted the Kuiper belt's abrupt edge before the cluster dispersed. This would mean the Kuiper cliff isn't just a curiosity, it's a fossil record of our Sun's long-lost family, preserved in ice and orbital dynamics for billions of years. What makes this frontier so fascinating isn't just the mystery, it's what solving it could reveal about our place in the cosmos. The outer solar system is the ultimate time capsule, holding clues to everything from planetary migration to interstellar visitors. Every new discovery, whether it's an oddly orbiting object like Sedna or a subtle gravitational anomaly, brings us closer to understanding whether we're alone in this quiet corner or sharing it with unseen giants. The Kuiper cliff isn't just where our solar system ends, it's where the real adventure begins. Galaxies aren't just drifting apart as the universe expands. Some are moving together in a mysterious, coordinated rush toward something we can't see. Astronomers call this phenomenon the dark flow, and it's as unsettling as it sounds. Imagine tossing a handful of leaves into a river, only to watch them all defy the current, sliding sideways toward some invisible drain. That's essentially what's happening with entire galaxy clusters, all streaming in the same direction at breakneck speeds, as if tugged by a force beyond the edges of our known cosmos. This isn't just a slight statistical quirk. The dark flow spans billions of light years, affecting thousands of galaxies with a motion so persistent that it can't be explained by the usual suspects: dark energy, dark matter, or even the gravitational pull of nearby superclusters. The most startling part, whatever's exerting this pull lies outside the observable universe, in regions of space so distant their light hasn't had time to reach us since the Big Bang. It's like feeling the breeze from a storm that's still over the horizon, a storm we may never see. So what could possibly be yanking galaxies on such a colossal scale? One radical theory suggests the dark flow might be evidence of a multiverse, that our universe is just one bubble in an infinite froth of others, and the gravity from a neighboring cosmos is leaking through, tugging at us like a magnet beneath a sheet of paper. Another idea points to relics from before the Big Bang, ancient structures or imbalances that survived the birth of our universe and still imprint their influence on the cosmic web. Picture a scar left by a wound that healed 14 billion years ago, still dictating how the flesh moves today. Then there's the spine-chilling possibility that the dark flow isn't a force at all, but a shadow, a distortion in space-time itself, warped by something so massive it bends the rules of physics. Some mathematicians have floated the idea of cosmic strings, hypothetical defects in the fabric of reality left over from the universe's explosive beginnings. These ultra-dense filaments, thinner than an atom but stretching across the cosmos, could theoretically twist space around them, creating currents that sweep galaxies along like leaves in a whirlpool. The implications are staggering. If the dark flow is real, it means our universe isn't the isolated, self-contained expanse we thought it was. Something out there, something beyond the cosmic veil, is reaching in and rearranging the furniture. And while we may never directly observe the source, its fingerprints are all over the sky, a silent reminder that the cosmos is far stranger, far grander, and far more mysterious than we ever imagined. The next time you hear that space is expanding evenly in all directions, remember, the universe might just be playing favorites, and we're only starting to guess why. Imagine an engine that defies one of physics' most sacred laws: no fuel, no exhaust, just pure thrust from seemingly nowhere. That's the tantalizing promise of the M drive, a controversial device that's been called everything from a revolutionary breakthrough to modern-day alchemy. At first glance, it looks deceptively simple: a tapered metal chamber where microwaves bounce around, supposedly generating forward motion without expelling any propellant. According to Newton's third law, this shouldn't be possible. For every action, there must be an equal and opposite reaction. So how can you push a spacecraft forward without pushing something backward? Yet, in lab tests spanning 2 decades, researchers have recorded tiny but persistent thrust signals that stubbornly refuse to disappear. The M drive's origins trace back to British engineer Roger Scheuer, who proposed the concept in the early 2000s. His design was met with immediate skepticism, and for good reason. If thrust could be created without propellant, it would upend centuries of established physics, rendering rocket fuel obsolete and opening the door to fuel-free interstellar travel. NASA EagleWorks Lab, a fringe group within the agency dedicated to exploring unconventional propulsion, took an interest and conducted their own tests. Their results, published in 2016, sent shockwaves through the scientific community. In a vacuum chamber, the M drive appeared to produce a whisper of thrust about the weight of a grain of sand, but enough to defy conventional explanation. Critics were quick to pounce. The measured thrust was minuscule, bordering on the noise floor of experimental error. Could it be thermal expansion of the device or electromagnetic interference skewing the results? Some argued that the microwaves might be interacting with the quantum vacuum, a seething sea of virtual particles that pop in and out of existence. But even this fringe theory struggles to explain how such interactions could produce net thrust without violating conservation of momentum. The scientific consensus remains clear: the M drive almost certainly doesn't work as advertised, yet like a ghost that won't stay buried, the anomaly persists. Independent labs in Germany and China have reported similar unexplained thrust, albeit under conditions ripe for false positives. What makes the M drive so compelling isn't just the technical debate, it's what it represents. This is a classic clash between the rigor of established science and the allure of disruptive innovation. History is littered with ideas dismissed as impossible, only to be vindicated later. Quantum mechanics and relativity were once heresies too, but science also has a long track record of impossible devices that turned out to be wishful thinking, from perpetual motion machines to cold fusion. The M drive sits squarely in this tension, a Rorschach test for how we weigh evidence against dogma. For now, the M drive remains a fascinating dead end, or perhaps a road not yet fully explored. While most physicists have moved on, a stubborn few continue tweaking the design, searching for a configuration that might silence the skeptics. Meanwhile, the dream it represents, a universe where the rules we know are just the tip of the iceberg, keeps the idea alive in the imaginations of engineers and sci-fi fans alike. Whether it's a measurement quirk or a glimpse of undiscovered physics, The M drive reminds us that the universe still has surprises up its sleeve, and sometimes the most tantalizing mysteries aren't in the distant cosmos, but right here in the lab, hiding in plain sight. Venus has always been the forgotten sibling of our solar system, a scorched, toxic world with surface temperatures hot enough to melt lead and atmospheric pressure that would crush a submarine. For decades, scientists dismissed it as a dead end in the search for life, focusing instead on Mars or icy moons like Europa. But in 2020, a bombshell discovery turned that assumption on its head. Astronomers detected traces of phosphine gas in Venus's upper clouds, a molecule that, on Earth, is almost exclusively produced by living organisms. Suddenly, the idea of life floating in the sulfuric acid skies of Venus didn't seem so far-fetched. Phosphine is a stubborn molecule. In nature, it shouldn't last long in Venus's oxygen-free atmosphere unless something is actively producing it. On our planet, the only known sources are anaerobic bacteria thriving in swamps and the guts of animals or industrial labs. No known geological or chemical process on Venus can account for the concentrations observed, at least not without invoking biology. The detection was met with equal parts excitement and skepticism. Could there really be microbes floating 50 kilometers above Venus's surface, surviving in droplets of water suspended in clouds of sulfuric acid? The conditions are extreme, but not impossible. Earth has its own extremophiles organisms that thrive in boiling hydrothermal vents, frozen Antarctic lakes, or radioactive waste. Some microbes even metabolize sulfur, a chemical Venus's atmosphere has in abundance. High in the planet's cloud decks, temperatures and pressures are surprisingly Earth-like, hovering around 30 degrees Celsius. It's a bizarre oasis in an otherwise hellish environment, a place where hardy life might cling to existence, shielded from the furnace below by a blanket of thick, swirling clouds. Yet the discovery quickly became a scientific battleground. Follow-up studies questioned the original data, suggesting the phosphine signal might have been misidentified sulfur dioxide or an artifact of telescopic interference. The team behind the initial findings stood by their work, but the debate raged on, highlighting just how difficult it is to study Venus from afar. Unlike Mars, where rovers can scrape rocks and sniff the air, Venus's crushing atmosphere and corrosive chemistry make direct exploration a nightmare. Even orbiters struggle to peer through its perpetual cloud cover. What makes this mystery so compelling isn't just the possibility of life. It's the reminder that we still know so little about our closest planetary neighbor. Venus might be Earth's twin in size and composition, but somewhere along the way, their fates diverged spectacularly. Did life ever take hold there? Could it still be hanging on, a ghostly remnant of a more habitable past? Upcoming missions like NASA Da Vinci and ESA's Envision aim to probe Venus's atmosphere and surface with unprecedented precision, searching for answers hidden in its toxic shroud. For now, the phosphine debate remains unresolved, a tantalizing maybe in the search for extraterrestrial life. But whether the signal was real or a false alarm, it's already achieved something remarkable, pulling Venus back into the spotlight. After years of neglect, scientists are looking at our twisted sister planet with fresh eyes, wondering what other secrets might be lurking in its acid-laced clouds. And if life really is there, surviving against all odds, it would rewrite not just the story of Venus, but the story of life itself. Galaxies are supposed to follow rules, dark matter's invisible scaffolding holding their stars in place, its gravity shaping their rotation and structure. But NGC 1052 DF2 didn't get the memo. This bizarre, ghostly galaxy floats through space like a cosmic rebel, defying everything we thought we knew. Most galaxies contain 30 times more dark matter than visible matter, yet when astronomers measured DF2 mass, they found almost none. It's as if someone forgot to add the glue that keeps galaxies from flying apart. The discovery sent shockwaves through astrophysics, because if dark matter isn't universal, our entire understanding of how galaxies form might need a rewrite. So how does a galaxy lose its dark matter, or never have it at all? One theory suggests a violent past. Picture two galaxies colliding, their dark matter halos sloshing like invisible oceans. In the chaos, DF2 could have been stripped bare, its dark matter ripped away by gravitational tides while the stars, more densely packed, stayed intact. It's like watching a car crash where the passengers walk away unscathed, but the vehicle's frame vanishes without a trace. Supporting this idea, DF2 isn't entirely alone. A few other oddball galaxies show similarly low dark matter, often near massive neighbors that could have bullied them in cosmic close encounters. But there's a twist. Some researchers argue DF2 might not be missing dark matter at all. Instead, our measurements could be wrong. Galaxies' masses are often inferred from the motion of their stars' faster orbits imply more gravity, and thus more unseen mass. But if DF2 stars are moving in unusual patterns, or if we're viewing it from an odd angle, we might be misreading the data. It's like trying to guess a car's speed by watching its shadow. The slightest error in perspective throws everything off. Follow-up studies have fueled the debate, with some teams confirming the dark matter deficit and others claiming it's an illusion, the most radical possibility. Dark matter isn't what we think it is. Most models assume it's a cold, slow-moving particle that clumps around galaxies like an invisible fog. But if dark matter interacts with itself or other forces in unexpected ways, it might not always behave predictably. DF2 could be a hint that dark matter is more complex, maybe even multiple particles with different properties, some of which avoid certain galaxies entirely. Alternatively, this could point to modifications in gravity itself, where the rules change on cosmic scales. What makes DF2 so thrilling isn't just the mystery, it's the reminder that outliers matter. Science advances when nature throws us a curveball, forcing us to question assumptions we didn't even realize we'd made. Whether DF2 is a cosmic accident, a measurement error, or a sign of deeper physics, it's a crack in the foundation of modern cosmology. And as telescopes like JWST peer deeper into its faint glow, we might just find that the universe's rulebook has more footnotes than we ever imagined. Deep in the cosmic static, hidden among the hum of distant stars and galaxies, there are bursts of radio energy so intense they outshine entire suns, and they last barely longer than the blink of an eye. These are fast radio bursts, or FRB, some of the most enigmatic signals in the universe. Imagine a flash of energy so powerful it could outshine 1,000 suns, yet so fleeting that if you weren't pointing a radio telescope in exactly the right place at exactly the right millisecond, you'd miss it entirely. The first FRB was discovered in 2007, buried in old telescope data like a cosmic afterthought. And since then, these bizarre pulses have taunted astronomers with their randomness and their sheer, inexplicable power. What makes FRBs so fascinating isn't just their energy, it's their unpredictability. Some burst once and vanish without a trace, like cosmic fireworks exploding in the void. Others, like the famous FRB 1211, repeat sporadically, flickering on and off with no discernible pattern. This inconsistency makes them maddeningly hard to study. It's like trying to solve a murder mystery where the clues appear at random, in random places, and the killer might not even be from this dimension. So where do these bursts come from? One leading suspect is magnetars, the universe's ultimate tantrum-throwing toddlers. These neutron stars, born from the collapsed cores of dead stars, have magnetic fields so intense they could strip the electrons from your atoms at 1,000 kilometers away. When a magnetar's crust cracks under the strain of these fields, it can unleash a scream of radio energy that ripples across the cosmos, a perfect match for the profile of an FRB. In 2020, astronomers got their first smoking gun when a magnetar in our own galaxy fired off a burst eerily similar to the distant FRBs we've observed. But not all FRBs fit neatly into the magnetar box. Some are too energetic, too frequent, or come from regions of space where no magnetar has been spotted. This has led to wilder theories like cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang. If these strings exist, their vibrations could theoretically produce bursts of energy as they snap and shift, like plucking a guitar string woven into reality itself. And then, of course, there's the elephant in the room. Could some FRBs be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might use bursts of focused energy to power interstellar light sails, creating pulses detectable across the universe. The real challenge lies in catching these bursts in the act. Modern telescopes like CHIME in Canada are now scanning the sky around the clock, turning FRB detection from a lucky accident into a routine event. With each new burst, we gather more clues, tiny shifts in the signal's polarization, slight dispersions in its frequency, that hint at the extreme environments they've traveled through. Some FRBs bear the scars of traversing dense magnetic fields, others the fingerprints of intergalactic plasma. They're not just mysteries, they're tools, cosmic probes illuminating the invisible structures of the universe. What's at stake isn't just solving a puzzle, it's rewriting our understanding of high-energy physics. FRBs might be the key to mapping the universe's missing matter or testing Einstein's theories in ways we never imagined. They remind us that the cosmos is still full of voices we're only beginning to hear, flashes of brilliance in the dark that demand we pay attention. And every time one crackles across our telescopes, it's a reminder. The universe is stranger, louder, and more alive than we ever thought possible. The universe is expanding. We've known that for nearly a century, but how fast it's growing has become one of the most heated debates in modern cosmology, a discrepancy so stubborn it's been dubbed the Hubble tension. Here's the problem. When we measure the expansion rate using nearby galaxies and supernova, we get one number. When we calculate it from the afterglow of the Big Bang, the cosmic microwave background, we get another. These values should align, but they don't. The gap might seem small, but in the precision-driven world of astrophysics, it's a yawning chasm, one that could force us to tear up the cosmic rulebook and start fresh. Let's break it down. The first method relies on standard candles, objects with known brightness like Cepheid variable stars and Type Ia supernova. By measuring how much their light has stretched as space expands, we can clock the universe's growth rate, a value called the Hubble constant. These local measurements consistently land around 73 kilometers per second per megaparsec. But when we turn to the cosmic microwave background, the faint echo of the Big Bang, the Planck satellite's data suggests a slower pace, 67. That's not a rounding error. It's a full-blown crisis, like two clocks ticking at different speeds in the same room. So what's causing the mismatch? One possibility is that we're missing something fundamental in our measurements. Maybe interstellar dust is dimming those standard candles, throwing off our calculations. Or perhaps supernova aren't as uniform as we thought, skewing the results. But after years of cross-checking, these explanations fall short. The discrepancy persists, gnawing at the foundations of cosmology. That leaves the far more thrilling alternative. Our models are wrong. The standard model of cosmology, lambda CDM, has been astonishingly successful. It explains the large-scale structure of the universe, the abundance of light elements, even the existence of dark matter and dark energy. But what if it's incomplete? The Hubble tension could be a hint of new physics, forces or particles we've yet to discover. Some theorists propose early dark energy, a mysterious field that briefly surged in the universe's infancy, tweaking its expansion just enough to leave a fingerprint in the CMB. Others speculate about dark radiation or even interacting dark matter, exotic variants that could subtly alter the cosmic growth rate. Then there's the most radical idea of all, that the tension isn't a flaw but a feature. Maybe the universe isn't as uniform as we assume. If we're living in a local void, a cosmic bubble where matter is sparser than average, the expansion rate here might genuinely differ from the broader cosmos. It's like measuring the tides in a bathtub and assuming they reflect the entire ocean. Whatever the answer, the Hubble tension is more than a technical hiccup. It's a rare crack in the armor of our understanding, a glimpse of the unknown lurking behind the equations. Resolving it won't just settle a debate, it could unveil entirely new chapters in physics, rewriting our story of the cosmos. And until we do, every measurement, every observation carries a whisper of doubt. Are we seeing the universe as it truly is, or just the shadows of something deeper? What if death isn't the end, but just a path you never take? This is the spine-tingling promise of quantum immortality, a thought experiment so bizarre it turns the concept of mortality on its head. In the many worlds interpretation of quantum mechanics, every possible outcome of an event spawns a new universe, branching endlessly like an infinite tree of reality. Here's the unsettling part. From your subjective perspective, you'd only ever experience the branches where you survive. No matter how unlikely, there's always a timeline where you narrowly escape death, meaning consciousness might never encounter its own end. Picture this: you're in a high-stakes game of Russian roulette, pulling the trigger again and again. In most universes, the bullet fires and your story ends. But in a vanishingly small fraction of realities, the chamber clicks empty each time. From your point of view, you'd only ever perceive those rare, lucky branches. To an outside observer, you'd almost certainly be dead, but to you, it would seem like impossible survival. This isn't just theoretical sleight of hand. It's a direct consequence of treating consciousness as a quantum process, where the observer's experience is inextricably tied to the branching paths of reality. The implications are dizzying. If quantum immortality holds, aging might not be the inevitable fade to black we fear. Instead, you'd always find yourself in timelines where medical breakthroughs, freak accidents, or sheer luck keep you going, pushing death's horizon further away. Of course, this doesn't mean you'd live forever in any classical sense, just that your subjective experience would never include the finality of death. The universe wouldn't feel like a miracle. It would just be, with every moment you're alive, reinforcing the illusion of continuity. But here's where it gets ethically thorny. If every choice spawns universes where all outcomes play out, does personal responsibility lose meaning? Could someone gamble recklessly, trusting they'll always land in a timeline where they win? Philosophers argue this mindset collapses under its own weight. After all, while you might subjectively survive, countless versions of you wouldn't. The emotional toll on loved ones in those alternate realities remains horrifically real. Quantum immortality doesn't erase suffering, it just shifts the perspective. The paradox also forces us to confront the nature of consciousness itself. Is awareness a continuous thread, or just a fleeting pattern that emerges in certain branches? Some theorists suggest this could explain eerie cases of luck in near-death experiences. Those stories of people surviving against all odds might not be flukes, but inevitable in a multiverse where every possibility unfolds. Others counter that without empirical proof, quantum immortality remains a metaphysical curiosity, more philosophy than physics. Yet even as a thought experiment, it lingers like a shadow. If consciousness truly is tied to quantum outcomes, then death might not be a wall, but a doorway. One you simply never walk through. And while we'll likely never test this idea directly, it serves as a humbling reminder. The universe might be far stranger than our intuitions allow, and the nature of existence far more elusive than we ever imagined. In the vast tapestry of the cosmos, few stars have captured our imagination like KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, this unassuming flicker of light became an overnight sensation when astronomers noticed its bizarre behavior. Unlike most stars, which dim in predictable rhythms from orbiting planets or pulsations, Tabby's star dims erratically, sometimes dropping in brightness by a staggering 22% before snapping back to normal. It's as if something colossal and irregular is passing in front of it, blotting out its light in fits and starts. When the Kepler Space Telescope first spotted these strange dips in 2015, the internet erupted with speculation. The most tantalizing theory, alien megastructures, specifically a Dyson swarm, a hypothetical array of solar collectors built by an advanced civilization to harness their star's energy. Imagine a vast network of orbiting panels or habitats, so enormous they occasionally eclipse the star itself. It's a concept straight out of science fiction, but for a brief, exhilarating moment, it seemed like science might be catching up. Of course, extraordinary claims demand extraordinary evidence, and astronomers quickly got to work debunking, or at least tempering, the hype. The leading explanation now points to dust. Not ordinary dust, but colossal, uneven clouds of it, possibly from a shattered comet or a disintegrating planet, swirling around the star in chaotic orbits. This dust wouldn't block light uniformly. It would clump and scatter, creating the erratic dimming patterns we observe. Supporting this, further studies revealed the star's light dims more at certain wavelengths, a telltale signature of fine particles rather than solid megastructures. Yet Tabby's star refuses to be neatly categorized. Even after years of scrutiny, it keeps throwing curveballs. In 2017, it dimmed again, this time in a slow, dramatic fade that lasted months, unlike anything seen before. Then in 2021, astronomers caught it brightening unexpectedly, as if some unseen force had cleared the obscuring debris. These wild fluctuations suggest the dust isn't just passively drifting, something dynamic is stirring it up. Could it be a family of exocomets caught in gravitational turmoil, a newborn planet smashing through asteroid belts, or something even stranger, something we haven't yet imagined? What makes Tabby's star so compelling isn't just the mystery, it's the way it challenges our assumptions. Most cosmic oddities eventually settle into familiar frameworks, but this one lingers on the edge of explanation, teasing us with possibilities. It's a reminder that the universe doesn't owe us clarity. Sometimes the most profound discoveries aren't the ones that answer our questions, but the ones that keep us asking. Whether it's dust, aliens, or some cosmic phenomenon we've yet to name, Tabby's star stands as a beacon of humility, a proof that even in an age of advanced telescopes and AI, the cosmos can still surprise us. And that's what makes astronomy endlessly thrilling. Not just the answers we find, but the mysteries that remain, glowing faintly in the dark, waiting for us to look closer. The universe looks chaotic at first glance, stars scattered like grains of sand, galaxies drifting in the void, but zoom out far enough, and a breathtaking pattern emerges. Imagine a spider's web spun on a cosmic scale. its silken threads stretching hundreds of millions of light years, with galaxies clinging to them like dewdrops. This is the cosmic web, the hidden skeleton of the universe, and its architect isn't stars or gas, but something far more mysterious: dark matter. You can't see this web directly. Its threads aren't made of anything that emits or reflects light. Yet its gravitational pull is so powerful that every galaxy, every cluster, even the voids between them are shaped by its invisible hands. Supercomputer simulations reveal its structure in stunning detail, a labyrinth of filaments intersecting at dense nodes where galaxy clusters glow like cities at night. Without this scaffolding, the universe as we know it wouldn't exist. The Milky Way didn't just form randomly. It was born along one of these dark matter highways, a cosmic freeway guiding the birth of stars. So how did this web come to be? The story begins in the universe's infancy, when the first ripples of density flickered through the primordial soup of particles. Dark matter, unaffected by the radiation that buffeted ordinary matter, began clumping first, its gravity drawing gas and dust into its embrace. Over billions of years, these tiny seeds grew into vast filaments, with galaxies forming brightest where the threads crossed. It's like watching frost crystallize on a window, random at first, but gradually revealing an underlying order. The cosmic web isn't just a relic of the past, it's still evolving. Galaxies are pulled along these filaments like commuters on a subway, streaming toward intersections where clusters collide in slow-motion fireworks. Even the emptiest voids, the web's gaping holes, play a crucial role. Their lack of gravity allows the universe to expand faster at their edges, stretching the web's threads ever tighter. Yet for all its grandeur, the cosmic web taunts us with its invisibility. Mapping it requires ingenious tricks, like watching how distant galaxies subtly distort the light of objects behind them, a phenomenon called weak gravitational lensing. These distortions trace the web's outline like shadows on a cave wall, revealing where dark matter's grip is strongest. Other clues come from the faint glow of hydrogen gas strung along filaments, illuminated by the ultraviolet light of quasars, or the way galaxies align like compass needles pointing to unseen magnetic fields. What's most humbling is realizing how much of the universe's structure operates in the dark. The cosmic web isn't just a curiosity, it's proof that the visible cosmos is just the glittering tip of an iceberg, with dark matter's invisible architecture holding everything together. And as we peel back its layers, we might just find the answers to cosmology's biggest questions: how galaxies assemble, how the universe expands, and what secrets still lurk in the spaces between the light. What if the universe isn't the ultimate reality, but something closer to an ultra-advanced video game? This is the unsettling premise of the simulation hypothesis, the idea that our entire existence might be nothing more than lines of code running on some unfathomable computer. The concept isn't new. Philosophers like Nick Bostrom have formalized it, and tech visionaries like Elon Musk argue the odds we're living in base reality are astronomically low. But what makes this theory so provocative isn't just its sci-fi appeal. It's the eerie possibility that if we are in a simulation, there might be subtle cracks in the facade, glitches in the cosmic code that reveal the truth. Think about the way video games render graphics. To save processing power, distant objects often lack detail until you zoom in. Could the universe operate the same way? Quantum mechanics already shows particles don't have definite states until observed, as if the simulation conserves resources by only rendering reality when someone's looking. Then there's the speed of light, nature's ultimate processing limit. No signal, no interaction can exceed it, almost like a built-in buffer preventing the system from crashing. Even mathematical constants, those unchanging numbers governing physics, might just be parameters hardwired into the program. But how could we ever test something this radical? Some physicists propose hunting for literal pixels in space-time, evidence that reality has a finite resolution at the smallest scales. Others suggest searching for computational shortcuts, like rounding errors in the laws of physics. Imagine if, deep in the decimals of gravitational equations or quantum probabilities, we found repeating patterns like the digital equivalent of a fingerprint left by the simulator's algorithms. There's even a moonshot effort to engineer a simulation shutdown experiment, a shock to the system so extreme it forces a diagnostic response, like triggering a blue screen of death in the cosmos. Of course, the simulation hypothesis has its skeptics. Many scientists dismiss it as unfalsifiable, a clever thought experiment with no way to prove or disprove it. If the simulation is flawless, how could we ever perceive outside it? And if it isn't, wouldn't the creators patch any glitches we discover? Others argue the idea is narcissistic, a modern twist on creation myths where humans imagine themselves as the central project of some higher intelligence. Yet the theory persists not because it's provable, but because it reframes existential questions in ways that thrill and terrify us. If we're living in a simulation, does free will exist, or are we NPCs following a script? Are suffering and joy just data points in some alien experiment? And if the simulation can be shut down, should we fear the off switch? The simulation hypothesis doesn't just blur the line between science and philosophy, it obliterates it, leaving us with a dizzying thought. The universe might not just be stranger than we imagine, but stranger than we can imagine. And until we find that telltale glitch, we're left wondering, is reality real or just really good code? Most of the universe behaves in ways we can categorize: particles with definite mass, waves with predictable frequencies, objects that obey the tidy laws of classical physics. But what if there's something stranger lurking in the equations? Enter unparticles, a hypothetical form of matter so bizarre it doesn't play by any of the usual rules. Proposed by physicist Howard Georgi in 2007, unparticles defy the very framework we use to describe reality. They're not quite particles, not quite waves, but something in between, a kind of quantum uncanny valley where the familiar breaks down. The magic and madness of unparticles lies in their scale invariance. Normally, particles have properties that depend on the energy scale you're observing them at. An electron, for instance, behaves differently in a hydrogen atom than it does in a particle collider. But unparticles don't care about scale. They look and act the same no matter how close or far away you examine them, like a fractal that repeats its pattern infinitely whether you zoom in or out. This means they don't have a fixed mass or size in the traditional sense. Instead, they exist in a fuzzy, indeterminate state, smeared across space and time in a way that makes even quantum particles seem downright orderly. So where would such a thing come from? Georgi's theory suggests unparticles could emerge from a hidden sector of reality, a shadowy realm of physics beyond the standard model where forces and particles interact in ways we've never observed. Imagine a parallel universe with its own rules, but one that occasionally leaks into ours, leaving fingerprints in the form of these enigmatic entities. If they exist, unparticles could be the missing piece in some of physics' greatest puzzles. Dark matter's gravitational grip on galaxies, for example, might not come from weakly interacting massive particles, WIMP, or actions, but from clouds of unparticles drifting unseen through space. Or they could help bridge the chasm between quantum mechanics and gravity, offering a path to the long-sought theory of everything. The real challenge is figuring out how to spot them. Unparticles wouldn't leave tracks in a detector like protons or electrons. Instead, They'd reveal themselves through subtle anomalies, tiny deviations in the way particles scatter off one another, or unexplained gaps in energy distributions during high-energy collisions. It's like trying to find a shadow in a dark room by watching how other shadows move. Experiments at the Large Hadron Collider and future neutrino observatories are on the hunt for these anomalies, sifting through mountains of data for the faintest hint of something off. What makes Unparticles so thrilling isn't just their potential to solve mysteries, it's how they force us to rethink what matter is. For centuries, we've categorized the universe into neat boxes: solid, liquid, gas, particle, wave, matter, energy. Unparticles laugh at those boxes. They're a reminder that reality might be far weirder than our textbooks allow, and that the next revolution in physics could come from the places we least expect. Whether they're out there or not, Unparticles represent the spirit of scientific exploration, pushing into the unknown, even when the unknown pushes back. From holographic realities to cosmic voids, these 35 insights peel back the curtain on a universe that continually defies our expectations. What we've uncovered isn't just a collection of oddities, it's a testament to how little we truly understand. The cosmos operates on scales and in ways that stretch our imagination, from particles that communicate instantaneously across galaxies to forces that rewrite the rules of time and space. Each mystery we've explored, whether it's the phantom pull of the Great Attractor or the eerie silence of the Fermi paradox, doesn't just challenge our knowledge, it redefines what we thought was possible. This isn't a universe of cold, empty darkness. It's a living, breathing enigma, pulsing with unanswered questions and hidden connections. Consider how black holes might birth new universes in their depths, or how the very fabric of reality could be a projection from the edge of existence. Even the emptiness of space isn't truly empty. It's a seething quantum foam, a cosmic web of dark matter, or perhaps the substrate of an unfathomable simulation. The more we learn, the more we realize how much remains just beyond our grasp. What makes these discoveries so thrilling isn't just their strangeness, it's the reminder that exploration is never finished. Every generation believes it's on the verge of solving the universe's biggest puzzles, only to uncover even deeper layers of mystery. The work of scientists, astronomers, and curious minds everywhere isn't about reaching an endpoint. It's about stepping onto a path that stretches infinitely forward. And that's the real beauty of it. The universe isn't a puzzle to be solved, but a story that never stops unfolding. So what's next? Maybe you'll be the one to spot the next anomaly in telescope data, or to propose the theory that cracks open a cosmic secret. The journey doesn't end here. Dive into the comments and share which insight resonated most with you. Was it the haunting silence of alien civilizations, or the mind-bending possibility that time itself is an illusion? And if you're hungry for more, don't forget to subscribe. The universe has endless surprises in store, and together we'll keep uncovering them, one mystery at a time. The greatest adventures lie ahead. Where will your curiosity take you?